Welcome back to linear algebra. In this video, we're going to be looking at null space and singular matrices. I can barely get my head out of the way of the title. Sorry about that. Just like row and column space, null space is one of the most important features of a matrix. The properties of the null space of a matrix will help us determine when systems of equations have solutions. They will help us determine, it's over here, it will help us determine when a matrix is singular. If I can point towards the title, sorry, my system here is cutting my hand off, making pointing very difficult. But the null space will help us determine whether a matrix is singular or not. It will help us determine whether a system of equations will have solutions or not. And it's also going to allow us to prove a result that you've learned about since high school algebra. So without further ado, let me get my head out of the way and let's jump in here. The null space of matrix A is the solution set of the homogeneous linear system AX equals 0. I said that along with row space and column space, null space was one of the fundamental vector spaces of a matrix. Row space and column space were kind of obvious. They are formed as linear combinations of vectors. So they are, of course, vector spaces. Null space is a little bit less obvious, but it is also the case that if you have two vectors, a linear combination of those vectors is also going to be a solution. All right, so let's let A be an m by n matrix. And the solutions to a system, a linear system formed by an m by n matrix, is going to be n-dimensional vectors. So null of A is a subset of Rn. We also know that any matrix times the zero vector will give us the zero vector. So that means that 0 is in the null of A. And if I have two vectors u and v in the null of A, then that means that A times u is 0 and A times v is 0. Again, that's the definition of the null of A. So if I take a linear combination, A times C1U plus C2V. I can distribute that. And get the zero vector. So a linear combination of vectors in the null of A is also in the null space of A. And that is enough to prove that null of A is a subspace of Rn. A vector space which is a subset of Rn and uses the same operations as Rn. Not a lot to state on this. Row equivalent matrices have the same null space. I mean, of course they do. The whole idea of row equivalent matrices was a tool to solve a linear system. And so using row equivalent matrices, they have the same solution, and the null space is the set of solutions. So stating it is useful. That's a fact that we will make use of later on in the course. But if you take just a minute to think about what the null space means and what row equivalent matrix means, you'll wonder why we even had to state this as a theorem. The point of elementary row operations is to form a new linear system with the same solutions. So if you perform elementary row operations, you get an equivalent matrix or a row equivalent matrix, and it has the same solution, and the null space is the set of all solutions. So I should stop beating a dead horse. Right. The nullity of A, which is written as a function that literally just writes out the word nullity. The nullity of A is the dimension of the null of A. So if we have a matrix, we should be able to find its null space. And once we know its null space, we can use that to write its nullity. So let's consider the matrix that we've looked at in the previous video. Let's get rid of that extra bit. Let's slide this bit over. So we have here that matrix A is this horrible, nasty mess. And I want to find the null of A. And then use that to find the nullity of A. So I want to solve the system AX is equal to 0. Taking matrix A, I can turn it into an augmented matrix by introducing a column, which is just a bunch of zeros. And normally, I can't just do this, but whenever you do any elementary row operations, a column of all zeros stays a column of all zeros. So performing elementary row operations will eventually take this matrix to the row echelon form that looks like the row echelon form we calculated in that previous video, but with a column of all zeros to make it an augmented matrix. So that gives us the solutions that we have here. We can make this a little bit easier on ourselves. This time it is worth taking the row echelon form and turning it into reduced row echelon form. I'm going to start by working with row 3 to get those last two columns to be, or the one column near the end to be 0. So if I take row 1 and I subtract 5 times row 3, 5 minus 5 times 1 is 0. 4 minus 5 times 5 is 4 minus 25, which is negative 21. Then we've got the 0 column. Then we take second row plus 2 times the third row. Negative 2 plus 1 times 2 is 0. Negative 6 plus 2 times 5 is negative 6 plus 10, which is 4. The last two rows are boring. All right, then one more step. Let's take row 1 minus 4 times row 2. So the 1, the negative 3 stays the same. 4 minus 4 times 1 is 0. Negative 2 minus 4 times 3 is negative 2 minus 12, which is negative 14. 0 minus 0 is 0. Negative 21 minus 4 times 4 is negative 21 minus 16, which is negative 37. Not too much happens in the last couple of rows. All right. But in doing this, we get a nice system of equations. I guess x1 minus 3x2 minus 14x4 minus 37x6 equals 0. We've got x3 plus 3x4 plus 4x6 is equal to 0. And we've got x5 plus 5x6 is also equal to 0. Rewriting this, I get it looks like x1, x3, and x5 are the only things that are actually of interest here. The rest of these are going to be free parameters. So let's go ahead and name all of our free parameters. T, U, and V seems like good names. And solving for x1, I'm going to get 3t plus 14u plus 37v. Solving for x3, I'm going to get negative 3u minus 4v. And solving for x5, I'm going to get negative 5v. Splitting this up, I can write this as 3, 1, bunch of zeros, t, 14, 0, negative 3, 1, couple of zeros, u, and 37, 0, negative 4, 0, negative 5, 1 times v. The solutions here are linear combinations of these three vectors. These three vectors are linearly independent, so the nullity of A is the span of those three vectors. And because those three vectors must be linearly independent because we got that matrix into reduced row echelon form, the nullity, are those three vectors form a basis. The dimension of the null space is 3, and that's what we call the nullity. It is, in fact, a complete coincidence that the matrix that I created by writing down a bunch of random numbers has the same nullity as it does rank. That doesn't usually happen, but those two values are always related. For an m by n matrix A, if you add the rank of A plus the nullity of A, you get n, the number of columns in the matrix. And the reason for that is that in row echelon form, each column of A either does or does not contain a leading one. And the rank of A is the number of columns which do contain a leading one in your row echelon form. When you are solving the homogeneous linear system AX equals 0, you are always able to fix values for each of the columns which contain a leading one, or for the variables which correspond to each of the columns with a leading one. Right, so in the homogeneous system AX equals 0, each column which does not contain a 1 represents a free variable. If I scroll up to the solution I just came to. Right. I looked at my 6 columns. I turned it into a system of 3 equations. And I said that I would be able to write equations solving for the first variable in each of those, which is the variable which corresponded to a leading 1 in the system. The other variables are what I turned into the free parameters. I used t, u, and v. And those free parameters were the things I used to separate out that solution into a linear combination. So the number of free parameters in the solution to AX equals 0 is the nullity of the linear system. Every column which contains a leading 1 counts towards the rank. Every column which does not contain a leading 1 becomes a free parameter and counts towards the nullity. In total, there are n columns. And since each column either does or does not contain a leading 1, no columns get counted twice, no columns get missed. So rank plus nullity is equal to n. That takes us to perhaps my favorite theorem to prove in this course. Let A be an M by N matrix and consider the linear system AX equals B. Remember, because A has M rows and N columns, that means that we are looking at a system of M equations in N unknowns. If M is greater than N, then we say that the system is overdetermined. And an overdetermined system may be inconsistent. I have to say M here because there's always the possibility that some of the equations in the system are redundant. That happens. If M is less than N, the system is underdetermined and may have infinitely many solutions. Again, I have to say may here because you can very carefully construct a system that simply has no solution no matter what, which is kind of boring, but it is something to consider. This is the result that you learn in high school algebra. If you have a system of M equations, or if you have N unknowns, you need N equations in order to satisfy all of your unknowns. If you have too many equations, you put too many constraints and you tend to lock out any possibility of a solution. If you put too few constraints, then you don't have enough information to solve the system. And the reason for this to be the case is exactly that theorem on rank and nullity. First of all, since M is bigger than N, in the first case, the rank of our matrix must be less than M, which means that the column space of A is not the entire set Rm. And that means that there are possibilities for vector B that are not in the column space of A. And if they are not in the column space of A, then there is no solution. Right? Again, it's always possible that you have redundancy. That's why the theorem says may and not will always. But it makes it very likely that you end up with a situation that is broken. In the second case, since M is less than N, we have that the rank of A is less than N, right? Rank of A is always at most the smaller between the number of rows and number of columns. But since the rank plus the nullity of A is equal to N, that means that the nullity must be bigger than 0. there is at least one dimension to the null space. That means that there's at least one free parameter to the solution ax equals 0, which means that there are infinitely many solutions to ax equals 0. And if you take a solution to ax equals 0 and you add it to a solution to ax equals b, well, a times that combination will give you 0 plus b, which is just b. So that means that there are infinitely many solutions to ax equals b as well. So with the vocabulary of rank and nullity in our back pockets, we can prove this theorem that you were taught in high school algebra. One last thing to talk about in this video. And that's our list of equivalent statements collection. We started into this a while ago. We had that statement that A has an inverse. The determinant of A is not equal to 0. And all the other equivalent statements that we've talked about in the past. The ideas of row space, column space, rank, and nullity give us several new statements that we can add to the list. The rows of A are linearly independent. The rows of A span Rn. So that makes a little bit more sense if I remind you that the list of equivalent statements works for an n by n square matrix. So there are n rows and n columns. Rows of A span Rn. The rows of A form a basis for Rn. The rank of A is not 0, but n. The nullity of A is 0. And then all these statements for rows can also be done for columns. The columns of A are linearly independent. The columns of A span Rn. The columns of A form a basis for Rn, and so on down the line. I'm not going to prove all of these, but many of these are fairly straightforward to get to. specifically the nullity of A. If A has an inverse, then the equation AX equals 0, X equals A inverse times 0 has a unique solution. And because that has a unique solution, the null space of A is just the 0 vector, which means that the nullity of A is 0, right? The set containing just the 0 vector is the 0-dimensional vector space. And then from here, because the nullity is 0, since rank of A plus nullity of A is n, that gives us that the rank of A is n. Then from here, if the rank of A is n, well, the row space of A is a subset of Rn, and the column space of A is a subset of Rn because A is an n by n matrix. Each row is a vector in Rn. A subset of Rn with dimension n is Rn. And since the rank of A is n, that means that the dimension of the row space is n. So the row space is in fact Rn. And for the row space to be Rn, that means that the rows span Rn. And since there are n rows and they span Rn with dimension n, they must form a basis because a set of n vectors that spans Rn is a basis for Rn. And if it's a basis, that means it's linearly independent. And if it's linearly independent, then we have everything else. And that's kind of where the proof goes, right? Not a complete formal proof. There's just entirely too much there, and it's not worth the time to get into in detail. But just a bunch of other properties. If we know any one of those things, let me scroll back up to the list of statements. If we know any one of these things, we get all of the others for free. Has an inverse, homogeneous equation, has a unique solution, determinant of A is 0, all the things about the column space. And having the column space is very nice. That means that AX equals B always has a solution because AX equals B has a solution whenever B is in the column space. If the column space is everything, then we're good to go. So a lot of tools here that are all equivalent. If you have any one of them, you know that you have a system that is solvable, and that really makes life easy. And that's what this course is all about. So with that, I will wrap up our discussion here, and I'll see you next time.